All right, good afternoon. Today we have what I think will probably be our last talk of the year, unless I get some more volunteers, from Jeronimo Bezerra from Florida International University and AMPATH. And he is going to be talking about a specific project that they've been working on called AmLight International or AmLight-INT, in-band network telemetry to support big data applications. So I will turn it over to you, Jeronimo.
Okay, good afternoon. Thank you, Jason. Thank you all that are joining us today. It's really a pleasure to be speaking this group here. Basically, this project is in a supplement, and I will provide more details about this. And the idea of what we're sharing this project, even though it's still like at the middle of the project, is to provide some exciting results we achieved so far. And then I think this community is going to really benefit from it. So basically, this is the outline. I want to talk a little bit about network monitoring, the limitations and technologies that we use today, give a brief introduction to network telemetry, the current network telemetry efforts that we're seeing in the IETF and Open Networking Forum, how we're doing telemetry in the AmLight, the use case for the big data applications, and the next steps for our project. So just a warm up. Right, all of you guys here in this call probably heard one of those questions before from your users. It's very common. You can even have those questions when you're using the network from home. So why am I not getting full bandwidth? Why my application achieving such poor performance? And where's the packet loss? Or even may I be placed outside of the firewall? And Jason leads handle this kind of questions pretty much every day. And those are not funny, but we have our own questions in relate to those problems. And the main thing that this is complicated to answer is that it's very tricky to have network visibility, performance, and isolate faults when you have like an environment that has production traffic, and then you need to answer this in real time. And if you have multi-vendor, it makes it even more complicated. So we have some of these questions ourselves. For example, we're testing here on a 100 gig link, and then there was one packet loss out of 1 million packets. So where is that packet loss? And we have situations if we don't know if there's a micro or just a burst happening in the topology right now. We barely know information about the network queues of the interfaces that we have, and if they are running close to the maximum capacity, if the flows that are using those queues were supposed to be in those queues, and what happened when we had the packet drop in the past because there was a network queue that was full, and who was using that queue at that time. And most of the complexity to do this sort of troubleshooting or answer those questions is because we, in my opinion, we're still leveraging very legacy tools, right? So we're still using traceroute, ICMP, SNMP, NetFlow, RMO, SFlow. Those are very good tools, but those operate in the samples or on-demand tasks, and they were not created to be troubleshooting real-time problems of the network. And we have things that are more like provide more information, like port mirrors or network taps. They operate out of band. They provide very good visibility, but they impose huge challenges in terms of CapEx and OpEx for scalability when you have an environment that has hundreds or even thousands of interfaces that you want to monitor. And even solutions that we heard lately, like Ethernet Operation Administration Maintenance, Ethernet OAM, or OpenFlow, that have some sort of statistics, they don't capture transient events. They don't detect microbursts, for example, and they don't help us to really narrow down what the problem is, or they help in some way, but not necessarily the most efficient or the most fast way. And one of the trends, something that we're seeing for most of the academic networks today, is that there's this trend of real-time big data applications that want to use our topology. And some of them, even with very restricted service level agreements or SLAs. And this is the use case I'll present later. But the problem is, and I have here in red, the real-time, because any attempt to track network state in real time can become like very complex and very expensive task. I don't know if you guys have had this kind of problem before, but if you try to get SNMP data or OpenFlow counters in an interval sub 30 seconds, that's not very desirable. In our case, we still use OpenFlow and OpenFlow. And we have seen switches and routers using SNMP, they actually crashed when you start pulling information every second. So, and every second is not even real time. But the devices were not made for this. If you use sampling technology, for example, SFlow, you get that information almost in real time, but it happens that you only get a sample. If you use NetFlow, you get information for the flow, which is exported after a few seconds. And if you want to do packet sniffing, yes, you can do this real time, but it's going to be extremely complicated for you to correlate events across the network. And that involves a huge CapEx and OpEx. And identifying microbursts or isolating packet loss in real time is not trivial with the current technology. We have seen vendors that have some sort of support like Jeronimo. They have on-demand and the possibility for you to track the queue of one interface, but that's far from what you actually need today. So going back to the title, the telemetry concept, it's not a new thing. It's been out there for 40, 45 years now. It's very popular in the medical and geology environments. And in the medical environment, they refer, the medical telemetry refers to those machines that the patients are hooked up to when they are at risk and they need to be continuously monitored. Telemetry in this case has very important metrics, and for the medical telemetry, those metrics could be cardiac rhythms, blood pressure, blood oxygen levels, and stuff. And telemetry also has imported properties, so accuracy, utility, the granularity, the sample rate, and alerts in case of a problem. Because when you use telemetry, you don't just want to collect the data, you also want to do something with that data in real time. And notification is a requirement, because if you have a patient that has a death risk condition, you don't want to notify the doctor 5 minutes after the patient passed away. You want to notify once you see that the blood pressure is changing or the cardiac rhythm is changing. And then leads us to network telemetry. So for the network telemetry is basically an extension of the network reporting more to higher granularity and sample rates combined with actionable metrics and alerting. So this definition, I provide the link and you guys will have access to the slides later. But this is not like a formal definition. This is a definition. In network telemetry technology, they have several characteristics. And the main one, in my perspective, that it's making all of this kind of solution like in band telemetry is that the possibility of streaming the data. So instead of you asking the device to give me the counters from that device, I want that device to send me that information as soon as an event happens. So that's called streaming network telemetry or streaming telemetry. In this case, if on an event that you predefined happens, then the switch notifies you right away, which means that you have access to that information right away, which means that you can react right away. So you can close the automation loop to even have a software that based on, I don't know, for example, CPU utilization, you change a configuration of a process, or based on an interface utilization, you move the flow to another interface. So this can be done when the device triggers that problem and not necessarily waiting for an interval or pulling the data from that device. So it's very important that this data gets normalized, so it has a proper format, it has the proper markup and everything, and encoded in an efficient way to be exported, because you want this to be consumed by applications in an easy approach, close to real time with enough precision. So that's the reason you need to model these telemetry reports. So in this case, if you notify an event at the moment it happens, that means that you can detect microbursts or queue utilization in a sub-second interval. You can monitor this, and the moment that the packet crosses the switch, you can notify this right away. And if you have that historical networks, all the network state and topology, you can do forensic troubleshooting, or you can do troubleshooting very easily, and you can do this close to real time. So this is an example when you have telemetry and you have microbursts, and you're getting that data in a millisecond interval. So what you're seeing here in the screen is like 60 milliseconds with three events of microbursts that last 4 milliseconds. And those microbursts were 3.5 gigabits per second. So you can see on the bottom, the average network utilization was 500 megabits per second. And then you have three spikes here that are microbursts that use, if you had like a 10 gig interface, that would be 35% of that interface. But if you have legacy monitoring, and I'm calling here 1 second legacy, but even though we most of the time do 30 seconds interval between SNMP gets, if you do a 1 second, that's what you're gonna see. Exactly what is exactly here. You have no idea if there was a microburst or not. You had no idea that there was an event at that point. And this is 60 seconds. So that's the kind of support that using streaming telemetry can enable for your network. The telemetry, the concepts surrounding telemetry, some of you are gonna go back to the documentation of the vendors saying, well, no, but Cisco had telemetry 10 years ago, Juniper had telemetry some years ago, Brocade has telemetry some years ago, but you're gonna see that telemetry is, there's no actual like a specification or a standard definition for what has to be supported. So sometimes we had vendors that expanded the SNMP OID, create like a monitoring of the CPU, you say, oh, now I have telemetry. So that's what the IETF, or the Internet Engineering Task Force and the Open Networking Forum are trying to standardize, is what is exactly the concepts surrounding telemetry. So in 2016, the P4, which is the programming language for data plane working group, they created this first use case for a P4 application, and that was the in-band network telemetry. So this was back in 2016. In 2016, the IETF, the Internet Protocol Performance Measurement, or the IPPM working group, was working and specified the same thing, and they first started with the proof of transit, which is very important for financial markets, that they have to map every single port and every single device that was used for a stock transaction, for example. And then they started specifying the data modeling, the data fields and the requirements, and how this is supposed to be implemented in terms of part of the in situ OAM data. So they define what are the data, there was the sequence, how many bits per field, and all of this. So this is still ongoing. Most of those are drafts at this point. They are not official RFCs. So you're gonna see a lot of definitions depending which source you use. IETF uses IOAM, in situ OAM, in-band OAM, and the P4 group, they use INT or in-band network telemetry. So those are used with the same purpose, is to instrument the network with more information, but not necessarily they describe how this is gonna be exported. So how the device make use of this, and how the device export that report. So this is the part, at least for the IETF, I see a gap. There's no specification for how to export the telemetry report, and the P4 leaves completely wide open. So it's up to you. So the focus of this presentation and the focus of our work was the P4 INT, the in-band network telemetry. And so the INT is an implementation just to record the operation information or the network state in the packet while the packet traverses that path, which means that if a packet goes from point A to point B and have 5 switches, each switch in the path will add the metadata that I am expecting, the telemetry information that I am expecting, and this packet start getting bigger and bigger with more information until you get to the last switch of the topology that extracts that information and send to the node B without as never happened. So this is a complement of the current solutions that we have for OAM. This is not was not meant to replace ICMP or replace a Ethernet OEM or any sort of counter. This is just a complement. The good thing is that because of, if you use P4, and some of you probably heard of this language, and I'm sorry I haven't created a slide to introduce P4, but if you use P4 to program the switch, the data plan that you're using, you have access to a lot of information from that device that you can add to the metadata according to your need. For example, if you have a switch, you can add a timestamp of when the packet arrived at that switch, the ingress port, the egress port. If you have like a P4 or you have OpenFlow, you can have the pipeline that was used, that's all the tables that were used. If you have a switch or router, you can see the queue buffer utilization or queue buffer occupancy. If you have a Wi-Fi router, you can report the Wi-Fi link power, even the battery utilization at that point, or sequence number or CPU utilization. So it's up to you to define what exactly you want to use. But the most important thing that I see from all those definitions are definitions that export the data directly from the data plane. Okay, what I'm talking about here is that picture, for example, SFlow or NetFlow, the data across the device, a main CPU of that device, which is the control plane, collect that information in the memory and then generates the IP packet and send to the collector. That is going to be remote in the topology. But that means that the CPU has to get involved in getting that data from the data plane, packaging that, and sending. And then if you use a sample rate that is 101, you're going to kill the CPU because those CPUs were not made for this. But if you do this directly from the data plane, which means you encapsulate it directly from the same CPU that forwards the traffic, that means that you can track or monitor or evaluate every single packet at line rate. And I'm talking about 100 gig flows where you monitor all those 800,000 packets per second that are part of that flow. Okay, and this figure here just gives like an idea of a representation where the metadata goes between the header and the payload. But I'm going to go with more details with that. So when the INT use case was created by the P4 work group, they had 4 questions in mind, right? The first one is, how did this packet get here? So what was the sequence of network devices the packet visited or traversed along its path? It has to be independent of the technology. So it doesn't matter if you have a lag, I want to see the lag port member. If it is ECMP, I want to see the interface. If it's a layer 2 topology, I want to see which switch, which port. So I want to see what was in the TCAM at that specific point in time. So, and the other one was, why is this packet here, right? So what happened in my topology that led that packet to the where it is right now? So what were the rules that were implemented by the OpenFlow entries or the TCAM entries or the P4 entries that forced that packet to get to the point where it is right now? So sometimes for proof of transit for the financial market, this is very important. How long was this packet delayed? So you all know what jitter is, right? It's the variation of the delay. So where is this, why there is a variation and where is this variation? So this variation is occurs because of all the buffers you have in the topology. So every device, including the nodes, have memory, and they store that data in the memory before they do the conversion from one medium to the other one, from, for example, the electrical to the optical. From you have multiple buffers. You have a buffer to receive that data at the nodes. So depending on how those buffers are used, the conditions or the occupancy, you're going to see a different delay, which means that at the end you have a different jitter. So the idea is that I want to see which device in my topology introduce that jitter. So this is something the INT wants to answer. And the next question is, okay, so I see that and that day, at that time, at that hour, that packet over there got delayed. But why was it delayed? What were the other flows or applications that were in the same queue exactly at the same time? So this, it's very good, for example, when you have QoS policies and you want to validate the policy to see if that packet was supposed to be in that specific queue, and then you can rebalance the topology depending of the queue utilization. Because one thing that you don't want to do is discard packets. You don't want to packet drops. It's bad enough that we have packet loss because of problems with the components, but packet drops is something that is manageable at some point. So we want to have at least information to help us to make the best decision. Jason, how are we going so far? Too fast? Good?
Perfect. No questions so far.
Okay, perfect. Let's move on. So how does INT work? So basically, consider from the left to the right. The first device that you see is like a router or a switch. That's called the source INT device. So that's the device that is going to receive the packet coming from the user. A normal Ethernet IPv4 payload packet is going to separate the TCP header to the payload, introduce the INT header, and then we'll introduce the INT stack. So the INT stack is the part of the packet where each device in the middle will add information about its own network state. And then it gets bigger, and the next switch makes it bigger, and the next switch makes it bigger until you get all those reports, until you get to the other side of the network where you have the INT sync, and the sync removes the report, all the metadata, sends to a collector, INT collector, which can be a normal machine, and then the packet flows through the destination node as if it never happened. So this is basically what happens. You can see that this happens per packet. Every packet is instrumented with network state information that can be used by the INT collector at the end. So before I start talking about our project, our INT project, let's talk about AmLight. So AmLight is, for those who are attending the same call 2 weeks ago, the brown bag 2 weeks ago, Kevin Thompson from NSF presented this NSF International Research Network Connections Program. And the AmLight EXP or AmLight Express and Protect is a project was funded, and this is the award number through that NSF IRNC program. So basically, the goal is to enhance the collaboration between the US and Latin America. And today we have around 680 gigabits per second of capacity between the US and the rest of Latin America. And this topology on the right reflects the current topology. You see that we have a few 10 gigs that we keep just as a backup because they are more reliable at some point. And everything else is 100 gig. We even have spectrum and a submarine cable that we decide what's going to be the capacity of each one of the links. So this topology that you see here on the screen, it is a SDN production infrastructure since 2014. And we presented a lot of times about this in Internet 2 Global Summits, Internet 2 TechX conferences. We started with OpenFlow 1.0, and then we moved to OpenFlow 1.3. Currently, we have points of presence in Florida, 2, one in Miami and Boca Raton. We have 2 in Brazil, 1 in Chile, 1 in Puerto Rico, and 1 in Panama. This topology carries everything that you might want, like from academic to commercial, from big flow to mice flows, everything IPv4, IPv6. We support inter-domain provisioning with the NSI. For those who don't know, is a way for you to stitching services, network services across domains. So you don't have to keep calling each NOC in the way, I need a VLAN from point A to point B. Now you can just use NSI for that. It is a consortium, and the AmLight Express and Protect is a consortium that involves FIU, NSF, the Brazilian Academic Network, the State of São Paulo in Brazil Academic Network, the Latin American Academic Network, the Chilean Academic Network, and the Association of Universities for Research in Astronomy, AURA. So a little bit about the use case. The main use case that we have at AmLight today is called the LSST, or the Large Synoptic Survey Telescope. It will be the biggest optical telescope in the world by the time it gets production. It has like an 8-meter wide lane. The total coverage area of the telescope is the size of a tennis court. And this will be production in 2022. Okay, it's going to be installed in northern Chile, and in one of those deserts over there. So the way how this telescope is going to operate is going to be in cycles of 27 seconds. So every 27 seconds throughout the night, of course, it's going to take a picture of the sky. It's going to process that picture, and it's going to generate all the transient alerts, which means everything that changed since the last picture is going to create a big package, and it's going to send all of this that sums up to 12.7 gigabyte to Illinois in the US. It's the NCSA, okay? But from every 27 second cycle, only 5 seconds are available for data transfer. That means that only 5 seconds of that window is going to be used for moving the data. Everything else is going to be taking or processing the picture. And just to give you an idea, every picture is expected to have like 10,000 events that are happening in the sky. So that's the reason the transient alerts are this big. And we're going to have multiple traffic types with different priorities. The LSST is not just the telescope. The control or the monitoring of the telescope is going to be done from Arizona. So it uses the network, the very same network that's going to be used to move the data. They have database synchronization, they have general internet traffic. So everything else that composes the network today, like Netflix, Facebook, all of this will be part of this topology. So we have to manage this accordingly. So the point is, what happens? What if the LSST doesn't manage to send its data in its 5-second data transfer window? For instance, because there was a packet loss, because there was a lack of capacity, because there was a lack of buffers, because there was microburst or DOS attack. The question is, if the data transfer window is missed, do you think AmLight engineering team will be able to fix whatever happened before the next one that takes place in 22 seconds? So I can bet you that no, that's probably going to be sleeping. The time that takes us for a wake up and get dressed and get a cup of coffee and do all the SSH is going to be much longer than this. So the point is, how many windows we're going to miss if we have to troubleshoot this manually and using the technology that we have today? So this is where the AmLight-INT project might be a solution. So basically, the AmLight-INT project is a supplement of the AmLight Express and Protect, and this is the award number that was funded November last year, but started become like a real thing in March this year, 2019. Which the goal was to deploy INT-capable devices in the topology, replace the current ones that we have that don't support INT, that don't support telemetry, for the ones that support. Deploy some INT collectors, which are basically 100 gig hosts with the software that collects this metadata. Develop a methodology to collect and export that data in real time to feed the controller and the automation, the closed loop automation, with information that to properly address the requirements that the LSST has and the network state that is being seen right now. And at the end, we expect to create like a telemetry report, design pattern to be used by other academic networks that have the same kind of need. So this diagram here on the right, it shows the locations we're planning to install switches in Chile, Brazil, Boca Raton, in Florida, Miami, Florida, and also we have a new POP where we connect to internet to that is in Jacksonville. So 3 of those POPs we have telemetry, INT collectors. Those INT collectors will receive that data directly from the switch, so they will be like back-to-back connected. And then they will parse that information, compress, and send to our local controller here, centralized controller in Miami, just the minimum information, getting down to a point, at least that's what I have in mind, that get to a point that says there is a problem or there is no problem. That's it. I want to have this kind of intelligence on those nodes to create this kind of feedback. Of course, this is kind of complicated, but we're going to try to get to that point. So I mentioned the 4 questions that the INT has when they create the use case, right? So how the packet got here, why is the packet here, where the delay, who was creating that delay. But when we start doing this last year, we realized, well, there are other things that have to be addressed, because P4, INT, and any kind of language, it's very good in the PowerPoint. Everything works in the PowerPoint. And then when you start moving this to the physical environment, where you have limitations of memory, limitations of CPU, limitations of I/O, then you have to be realistic and understand that even though the switch might support tracking every single packet of every single flow from all the interfaces, it might be complicated for you to parse all that data in real time, because a 3.2 terabit per second switch will generate around, what, 99 gigabits per second of telemetry. So you don't want to process 100 gig per second of telemetry per switch. So you have to define, and we will have to define, and we're trying to do this, is how many high priority flows can be handled. What is the impact of having INT in our network? Because we're talking about adding metadata means increasing MTU, extra delay for serialization. How do we dynamically enable the flows that we want to monitor? All right, so if you don't want to monitor Netflix and Facebook, how do we enable the monitoring just for LSST and AmLight-C, for example? One thing that I keep talking a lot of here is like real time, but what is the definition of real time, right? So there's a real time for a data center, there's a real time for when, there's a real time for an application. So we don't have this concept properly defined, but I'm estimating that real time is providing a feedback in less than 500 milliseconds, because the distances between Chile and the US. So how do we store and how we process multiple gigabits per second telemetry per switch? And how do we share this network state with the users? If the users want to have a visibility of the network, is that a way that I can create a way of feeding the user with that information in a useful way? Because the user doesn't want to process gigabits per second. He wants to use a few kilobits per second top. So the AmLight-INT project right now, it's a collaboration between FIU and NoviFlow, which is a manufacturer, a switch manufacturer that have been working with SDN for quite some time. And they have this platform called WP5132, which basically is this off-the-shelf switches that have the barefoot Tofino chip, and they create the operational system for that they call NoviWare. So those switches, they support the Tofino chip, which is a chip that is fully programmable with P4. It's a switch that has 3.2 terabit per second data throughput, which means 3200 gig ports, non-blocking, and they have a version for 6.64. And now there's the Tofino 2 that has 32 400 gig ports. And those are highly programmable. And NoviFlow supports OpenFlow 1.3 and 1.4.5. And 1.3 is the version that we use today, and they have the support for bidirectional forwarding detection, BFD, and link aggregation that we want to use. And they have released codes that we tried, so we have something in production. And then everything that is being done in partnership with NoviFlow is supposed to be generic in a way that anyone could use, which means there's nothing that is being developed just because of the LSST. We don't want to create a solution that only fulfills the needs from the LSST. We're on a solution that anyone could use. So the first results that we got in June, it was like we created a Wireshark dissector that basically parsed the report and printed using Wireshark. And then here you can see a report. And then we created the AmLight-INT collector, the first draft of version 0.1 in Python 3.7 that receives the report, saves to disks, prints on the screen, and sent to RabbitMQ queue to be consumed by other applications. Basically, yeah, it doesn't have much intelligence. It's just a conversion from binary, from bytes to JSON. So this you can see here on the screen, the metadata, all those fields here are equivalent to 12 bytes. And then on the bottom, you see the INT metadata stack where you have two switches. And from each switch, you can see that you have the switch ID or data path ID, you have the ingress port, the egress port, the ingress timestamp, and the egress timestamp in nanoseconds for you to calculate the the delay that that packet faced, the queue occupancy, and the QIT. So the hop latency is here, but it's not supported right now. And then you can see that this packet crossed 2 switches right now. And the other switch start from port 10 to port 1, and also use Q0, and there was also the queue utilization of 2 cells. And this is the first, just to give it an idea, this is, we did like an iPerf for 10 seconds, and then we zoom in for the first 7 milliseconds, just for us to see what was happening in that queue, because, well, 10-second data transfer with the IPF could easily get like to 3 million packets. So we just zoom into the first 7 milliseconds, and then you can see here what was the jitter created by that, per packet, by each one of the switches. The gray is one switch, the orange is another switch. And then the blue line that you can see, which is the equivalent to the right axis, y-axis, is the packet size. So you see that the packet is very small, then grows to 1400, and then keeps fluctuating because of the reports. And then you can see the jitter in nanoseconds. So this jitter is not something to be concerned. And then you have the occupancy. So what was the utilization of that Q0 for each one of the devices in the past? And then you can see at the beginning of the iPerf, there's a lot of communication to establish the test, and then start sending the packets. And all of this here is like 1 or 2, it's less than 10 milliseconds. And then you can see the buffer utilization per switch for that packet size. Okay, so then we start working in other tools. We start mapping the use cases. What exactly is the problem we're trying to solve? What is exactly the answer we're trying to answer, or the question we're trying to answer? And then how we're gonna use this in a more production way. So we start creating applications, documenting, and by October, we had the first application to consume the report that we call QTop. So QTop, for those who work with Linux, you probably heard of an application called Top or HTOP that shows on the screen the CPU utilization, memory utilization for that Linux machine. So the QTop is basically that view of a real-time snapshot of all the queues in the topology. And then we created this topology that you see here on the right side, where we have 400 gig nodes, 5 switches, the collector, and those are the port numbers. And then the idea is that node 4 on the far right and node 3 also on the far right, they will be sending data to those nodes on the left side. So the flow on the bottom will always be there, 56 gigabits per second nonstop TCP flow. And the one at the top is the one that we're going to be using for tuning to see what happens. And the goal is to see what happens with this interface that has the red arrow, which is the fan-out interface, or the interface, the upstream interface of the Novi3 that receives. Novi3 is going to receive data from 2 nodes, but it has to narrow down to just 1 pipe. Okay, so let's see what happens next. So this is one source, one destination, just the flow on the bottom, 6 gigabits per second. And then you can see that each queue from each switch, so those are the 5 switches, those are the 5 interfaces, and those are the 5 queues. You can see that it doesn't matter what the queue number is, we're going to monitor that. And you can see that all the queues have exactly the same utilization. So 115 cells translate to 9,000 bytes, which is the MTU, which means that that 60 gigabit data transfer always have 1 packet in each switch. That's pretty much it, no more than 1 packet. And then you can see here on the bottom, the hop delay, which means the egress timestamp minus the ingress timestamp. And you can see the average is the same, 1 microsecond, with the exception of the switch on the bottom, which is Novi3, because that's the one that has introduced the INT header. But again, this is just 1 microsecond extra, okay? So the behavior is, the theory that we had was like, we confirmed if all the components are the same speed, there's no need for us to do buffering this. So then we start sending more data from the nodes on the top, right? So now we have 50 gigabits from one flow, 25 gigabits for the other flow, And then on a NoviFlow, which is the switch that has the 2 nodes, then you start seeing buffering, of course, because now I have 2 inputs and I have 1 output. And then and we are seeing here the Q occupancy increasing 9 times. All the other ones, because the packets are already serialized, they don't change the behavior. Is 115 because they are going to receive 1 packet and going to send out 1 packet. But for NoviFlow, it has to address multiple sources and 1 output. I know some of you are going to have this question, but let me say this right away. The tool is only providing the data. Okay, so we don't have all the answers for why is this like this, because our theory to start with will be the buffer would be equivalent to 2 packets. Why there's 9 times more than why there's 9 times more than what we saw before. So now we're in the phase of now that we've seen this, we're trying to understand what this is happening. And then you can see here on the bottom that the hop delay increases 4 times. So even though the buffer is 9 times bigger, the buffer or the hop delay was just 4 times bigger. But don't forget that the switch on the bottom also has to create the header. And now there was something completely weird that we're still trying to understand. This we detected yesterday. And we detected this to create those slides, in fact. And because we have the NoviFlow is part of the project, they are also investigating this. So now we have both flows from the top and from the bottom. So going back to those flows in the green here to try to use as much as possible. Those are 100 gig nodes, but this is a 100 gig upload, right? So, and then we see that the switches at the end of the pipeline, or the switches that are far end of the topology, are the ones having a lot of buffering, like 24,000 cells, which leads to almost 1.6 megabyte buffer. But why is the 2 last switches in the topology have buffers? In theory, that's what I'm trying to confirm right now. They have exactly the same hardware and exactly the same software. So it was supposed to be seeing the same behavior in all the switches, except for the first one that has to do this realization, the buffering. But all the others were supposed to be packet in, packet out. So this is where we have right now under investigation. And these were amazed to see this, because if we're seeing this now, that means that probably we had this in the past, but we never had access to this kind of information. So even though some of you might be saying, yeah, this is very bad. No, this is very good. It's very good because now we have information. It is bad that we have the problem, but it's very good because now we can try to address the problem. Before, the switch was a black box. And you can see that the hop delay for this 1.6 megabyte buffer was almost 119 or 154 microseconds. So that's when you start seeing on the ping, because the ping was 0.088 milliseconds, and then suddenly increased to 0.400 or 400 microseconds. So now we saw that this is true, that this was happening. So the next steps that we have for this project, we still are at the half of it. We still have another year to go, is understanding these behaviors. So now we have to learn a little bit more about switches. We had to learn a lot about how the hardware works, how the switch architecture works. So now we have to understand why is this happening this way. And also we have to improve the INT collector's performance, because if you have this 99 gigabits per second resulting flow with 9,000 bytes, that means 5 gigabits per second of telemetry data. So that's a lot for just one flow, for just one switch, right? And we're kind of struggling with the Linux kernel to optimize this. We're missing some packets. So the next step is we're gonna use the P4 NICs provided by Metronome that can process this in the hardware. And these NICs will have the software that will do the processing of the report and only upload to the upper layers the situation that leads to a problem. We don't want to see everything. We want to see consolidated, or we want to see problem right away. We also have tools that we're integrating on InfluxDB Elastic. We're going to make all these tools open source as soon as they are ready for production. And we have a presentation about this project. Probably you guys are going to see almost the same slides, but maybe 1 or 2 new slides if we get information about those behaviors that we saw so far at the Internet 2 Technology Exchange, December 10th at 4:10 p.m. Okay, so I just want to acknowledge the team here, Arturo Quintana, our software developer, our PI, Juli Barra. We have a very good collaboration with the University of Passo Fundo in Brazil, but they are working with the P4 NICs that we have in our environment to address the LSST use case. So we have Alison and Pedro, 2 master's degree students working on that. They have amazing results. They are about to defend in December, and they are advised by 2 professors at the university, Dr. Schmidt and Dr. Trentin. And we have the Key to Z-Line integration. Key to Z-Line is the SDN controller that we use for our switches, and we are expanding that to support ANT. And the Quito developers at the University of São Paulo, State University of São Paulo, and the Academic Network of São Paulo that are working on this code to make our SDN environment ready for INT. So thank you again for your participation. Thank you, Jason, again for letting me talk about the project, and I'm open for questions and comments.
All right, well, thank you, Jeronimo. We did have 2 come in, actually 3, so I'll go in order here. The first one is from Jeremy. How do you manage MTU size as the INT stack gets bigger?
Okay, yeah, that's always the first question. So the Tofino chip has the MTU of 10,000. Okay, so, and we test this. We went all the maximum that the Linux can do it, which is 9950. In fact, we were not able to confirm that Tofino was 10,000 because the Linux was only 99,000, 9,900. And but the protocol itself, the P4 code and the INT specification, they have their own controls. So if they see that before they add metadata, they check what is the MTU of the output port. If the MTU is bigger than the total resulting packet with the telemetry, they don't add telemetry report, and they set a bit that says that the MTU was exceeded, so the collector knows that this happened. So then the collector can change the MTU of the port if that's possible, or it can decrease the MTU of the user interface, or it can, in some cases, decrease the size of the metadata, the amount of information that you're going to provide for the telemetry report. So yes, MTU is a problem, especially if you have equipment, legacy equipment in the middle of the topology that don't have like a huge MTU. For example, Brocade that only supports now 9,200, is 16. Yes, that gives you flexibility for 8 switches with providing metadata. Then if you have 9, you're only going to have 8. There are many publications out there on how to do this balance of which switches in the topology to add metadata to avoid this kind of situation. But in our environment, this is not an issue because the MTU of this box is 10,000. That means that we can easily add 44 metadata from 44 switches, even if the MTU is set to 9,000.
Okay. The second question is from Joe Breen. Are you looking to do correlation with other flow tech like SFlow, NetFlow, along with the INT P4 info for devices that might not support P4? For example, how do you envision getting info from endpoints like DTNs without a P4 NIC?
Okay, so there are 2 questions in there. The first question is if we're trying to do correlation. At this point, no, Joe, because we're still trying to validate the information that the switch provides itself in an INT format. This project, at least the first phase of it, doesn't have the resource to do this. It's a very good use case. I'm now inviting you to participate with us and help us to do this. We've done this before with OpenFlow, and we even had publications about this. But as if there's no more surprises, I think we're gonna end this project exactly with the scope that we predefined, but nothing, it doesn't mean that we cannot have a follow-up and continue doing this. For the endpoints that don't support P4NIC, so at this point, in this project, we're not engaging the DTNs. So the nodes are completely transparent to this project. We have ideas to bring those P4 and expand the data plane all the way to the DTNs. And we, from the tests and theories that we had before, this can be done without the P4NIC. You can do in the Linux kernel, you can program that kernel stack to add the telemetry header. This is not a big deal. So one thing that we envisioned in the past was the nodes, the DTNs will make space, will introduce the INT header, but will not provide any information because they don't have queues and anything. And then the next switch, seeing that there was an INT header, then the switch would just do the metadata. And then the last DTN, the remote DTN, will have the full packet of header and metadata, and that DTN will do whatever it wants with that information, or we can extract it before it gets to the DTN to our INT collector. So the INT provides you the capability of doing both things. You can export and at the same continue forwarding, and it's a matter now of what your hardware supports. So if you have metronome cards, you can do a limited number of activities. If you have Tofino, you have another limited number of activities. It depends a lot of the hardware you're using to do this.
Okay. And last question from Jorge. What are the pros and cons of NoviFlow with respect to edge core or other switches, also based on Barefoot's chip that you are aware of?
Oh, NoviFlow is a software company. NoviFlow uses edge core switch, uses Foxconn switch. I think there are 8 brands of off-the-shelf switches that use Tofino chip, and NoviFlow only does the software. They stack all the way to the hardware programmability to the interface. That could be OpenFlow, it could be, I think they have netconf, and I think they are close to have OpenConfig. But NoviFlow is just software. They use the same edge core switch you're talking about. The point that you have to see, if you buy the edge core switch directly, then you have all those NDAs that you have to sign to have access to the P4 runtime compiler, but then you have to do it all yourself. So it was our decision not to have, to do this in partnership with NoviFlow, because we don't have enough hands in our team to do the P4 code, validate all the possibilities, and then also do the collector side, and then give meaning to all that data. Do programmability using P4, the whole stack of functionalities that you might have in your network, it's extremely painful, especially at the moment of testing. And we have seen a number of security issues of even like traffic steering of people exploiting IP, the options field that was not properly set, and steering the traffic towards like a sniffer, for example. So we don't want to do P4 runtime ourselves right now, because we are more concerned about giving meaning to that data. But who knows, maybe down the road, P4 runtime would be a nice thing for us. But right now, we don't. So in this case, NoviFlow is just a software for us.
Okay. Well, that's all the questions that we had. So I'll thank you again, Jeronimo. Great presentation. If you can send me a copy of the slides, I'll make sure that those get posted. And sure. I will post this video as well. Everybody who's still on, thanks for joining. This is our last talk that I have scheduled for 2019 at this point. So if you do know anybody who'd be willing, or if you yourself are willing, please let me know and we'll get them scheduled for either later this year or early next. Hope everybody has a good rest of your week and has a good weekend, and we'll talk to everybody soon.
Thank you, Jason. Thank you all.